Okay. Hello, everyone. Uh, in last class, we just talked about some basic concepts relevant to the processes. You should know that the concept of a process can be defined as an instance of a program. It means you can have one program stored in the disk, and you can you can create a lot of processes based on exactly the same program. And for each process, it has its own address space and its own life cycle from the time you create it to the time you just terminate it. And during the life cycle, there are some different basic states for a process. It means maybe in during this period, the process is just created, and then this process is in the new state. And after that, if the process just gets everything uh, it needs in the memory, and the CPU schedule and the scheduler of the operating system just choose this process to use CPU, then the process can be in the state of running. And after this process uses up its allocated time slot, it has to get out of CPU and stay in memory uh, and wait for the next scheduling. So in this time, during this period, the process is in the ready state. So ready state means the only thing the process needs is the resource for computing is CPU. So this is the meaning of ready state. And also, if this during the execution of some instructions, if the process needs to get some response from the user, or the process needs to get something or wait for something to happen, at this time, we call this process as a process in the blocked state. So it means the process is waiting for some waiting for a specific event to happen. So during this among these three basic states of a process, I mean running, ready, and blocked, the process might have a lot of transitions among these three different basic states. And we just talked a lot about the cases that all of those four possible transitions happen. So that's basically all the important content we just discussed in the last class. And in this class, we're gonna learn something about thread, but we just need to we don't need to we don't need to dig deeply into the threads, because a lot of things related to threads are very similar to the processes. So we just need to understand the definition of the thread and the basic classical model for threads, and it's enough. The focus on this class should be put onto the third section of this chapter. I mean, IPC, interprocess communication. As I mentioned before, it's very important, also maybe the most important part for this course. So we need to pay more effort and time on this part. So before we move on to section 2, we should talk something about the last part of the first section. We just introduced the PCB, this very important structure for operating system to control, to manage all the processes in the system. And each process will have a PCB, process control table, to store all the information related to this process. And in the operating system, there is a special table with multiple process table entries for all the processes. And in each PCB, in each process controller block, you can find all of this important information, including the program counter, which just show us, which will show us where, the point the processes is executing, which instruction is just finished, and which instruction will be executed the next. So and also you can find a lot of useful information in PSW and stack pointer, etc. I just explained this last time in the last class, and I suggest you to understand all the you need to figure out all the items listed here, listed in this table, so that you can understand the way the operating system manage the process better. And for the last part of section 1, it's about the utilization of CPU. In the same computer, we can the operating system allows multiple processes running in the same computer, right? So it's very important for operating system to evaluate the utilization of CPU, but it's a very complicated problem. You have to track a lot of information, and basically we can just roughly compute the calculate the CPU utilization based on this equation. So you can just take a quick look on this expression, where the P means the probability that all the processes in the system are waiting for the inputs or output operations, and N is the degree of multi-programming, where the degree means how many processes are in the system at this moment or during a period. So you just need to be aware of this expression, which is used to roughly calculate the CPU utilization for the system. So that's all about the first section, and then let's move on to the second section about threads. Okay, threads are you can see there are much more parts in this section, but we just only mentioned 3 of them, and I think maybe it's enough for you to just understand why we need to use this definition about thread, why we use thread in the process, and also you just need to understand the contents of about the basic information about the basic information related to thread management compared with the information used to manage the process. And so we just need to focus on these two parts. And for the third part, it's just you just need to know it's a popular standard. Okay, so let's move on to the first part. In traditional operating systems, all the processes, they just have only one single thread inside its structure. But however, in nearly all the modern operating systems, they adopt the way to allow a process own more than one thread. So it means you can the operating system supports the process to have multiple threads inside. So the reason for the operating system to support such a setting is basically there are four reasons for this phenomenon. The first one is that in one process, usually we can have there are multiple activities. For example, if you are using the Word to edit some papers, some articles, you need to the users need to type some words, type something into the file, and the and the content in the file needs to be stored in the disk, and the content showing in the screen should be arranged by the process. Also, if you we just mentioned this example again. If you want to watch a movie on the computer, it's a process, right? As we mentioned a lot of times, if you double click that file, that movie file, the operating system will just create a process to handle all the all the operations on playing this movie. And inside that process, there are multiple activities. For example, you need to load the data, the movie file from the disk into the memory. You need to decode the part of the data file, and after you decode it, you need to show them. You need to output the result of the decoding on the screen and through the speaker, right? Basically, you can divide it into these three typical activities. And as the movie files, you are usually need a lot of need a big a great capacity to store them. So it's basically impossible to load all the data, all the movie file at the beginning of the creation of a process. We just move them part by part. For example, if you watch the movie from the beginning, so during the during the first second, maybe you just need to load the first one for the data related to the first minute of that movie, right? You don't need to load the whole 90 minutes or over 100 minutes of data. You just need to load a small part of that data file. And when you are when the operating system is encoding the first minutes of data of that movie file, at the same time, maybe the operating system can, not the operating system, maybe the process to play this movie can do another thing in meantime while okay, let me put it another way. So we just say there are three three activities in the playing process, right? You input the data into the memory and you decode the data and you output the data, right? Three basic behaviors, three basic activities. So while the process is decoding the first input, the first part of input data, it's possible to input the second part, of the movie data, right? And during while the process is decoding the second part of, I mean, you can just divide them into into the units of minutes. When the process is decoding the data for the second minutes of the movie, at the same time during the same period, the process can try to load the third minute of data, the third minute of data from the disk into the memory. And at the same time, also the process can output the first minutes of data onto the screen and onto that speaker, right? So you can see if we just divide one process into 3 threads, for this example of related to movie playing, if we divide it into 3 parts, into 3 threads, and inside of this process, during the same period, we can allow 3 activities happen in a parallel way, right? And obviously, in this way, the process can be executed in a much higher efficiency, right? So that's the main reason we need to use threads in the process. If we support a smaller unit, so if we support multiple threads in a single process, it's possible for this process to parallelly run multiple instructions for this single process, and it will just improve the efficiency of the execution. And you can imagine, you can think about more examples that we need to use multiple threads in a process. Maybe you can discuss with me after the class. Anyway, it's a popular way adopted by almost all the modern operating systems. So and this is the first reason, and I think it's the main reason. Moreover, we have some other reasons to support multiple threads in a single process. For example, if we use threads, you can see the threads. We just need to emphasize this tips first. So all the threads in the same process, they share the address space of the process. They share the same address space of this process. So it means when the operating system needs to manage the threads, the operating system doesn't need to worry about the address space, because all the threads in the same process, they just share the same address space. So if the operating system is managing the multiple threads from the same process, they just need to focus on the execution information about this threads. They don't need to manage all the manage different address space for different threads in the same process. It means the threads are lighter weight than processes because you need to the operating system has much less stops, has much less things to handle. So this is the second reason, and also if we use multiple threads in a process, we can get better I/O performance. You can imagine some processes with a lot of I/O operations. Sometimes it needs to input the data, input a large amount of data, and output a large amount of data, and we can divide it into multiple threads and handle them in a parallel way, and you can get better I/O performance. Also, it's useful it's very useful for those computers with multiple CPUs. If as I mentioned before, on this course, when we discuss kinds of basic principles about the operating system, we just have a very important assumption that there is only one CPU in the computer. But however, you know that in the computers, sorry. The modern computers, they just have they can set a lot of multiple CPUs. Even though maybe it has only one CPU, it's possible for them to have multi cores in this unique CPU, right? So it means from the hardware perspective, it just provides the possibilities to allow the process to be executed in a parallel way. If we don't use that, it sounds like we just ignore this way to improve the efficiency to execute the same this process, right? So if the hardware just provides us the possibilities to allow a process to be executed in a parallel way, then and we just make good use of this condition. We just divide one process into multiple threads and put them into the multiple CPU in a physically parallel way, and we can get the results much faster than we put this process in just one single CPU, right? So we just list some reasons here about why the operating system supports multiple threads in a single process. And during this, after we explained these reasons, I guess you already knows about the thread, the definition of the thread. The thread just you can see you can define a thread as how to say, a separate unit to be executed inside a process, and a process can be divided into multiple threads. Okay, let's just maybe we should jump over the abstract concepts and move on to the example about through these two concrete examples. Maybe you can understand about threads in a deeper. So these two examples, the first one is about the word processor, and I just mentioned it in the beginning of this class. Because when we edit some file based on this popular application word, we can roughly divide the operations into three parts. We can set three threads, and one thread is responsible to interact with the user, and the second one can be designed to reformat the file, because as long as you type something new into the file, and you can the content showing on the screen should be reformat, right? So the second one is responsible for this operation, and the third one we can use another one, the third thread, to to charge the operations about automatically saving the file to disk every few minutes. It can be done periodically. So basically, with these three threads in the same process, we can just the users don't need to wait for a long time while the third thread is how to say, is outputting the data to the disk, because it can be done background through the scheduler. So the users, maybe it feels the users feel like they just they can input a lot of characters without any waiting for the IO operations. But actually it's just how to say, it's just because the process adopts three threads to charge the three different kinds of activities. So you can use this word in higher efficiency. And for the second example, it's about a server process for a website. When for a website, especially a popular website, it has to handle thousands, millions, or maybe billions requests from the different terminals worldwide, right? So it's very important for the server of this popular website to respond the requests faster, sooner. And if if we just if we don't divide the process, if we don't divide the server process into multiple threads, it means during the same period, the the process can handle only one request from a specific user. So it's very slow, and it's not acceptable for the common users. So we just adopt this mechanism. We use we have in the server process, there are two types of threads. The first one is dispatcher thread. So this thread is used to read incoming requests from the network from all over the world, and decide which worker thread should be responsible to handle this request. There are a lot of worker threads inside this server process. So after the dispatcher thread get any request from the world, it just dispatch the work to to an idle worker thread very soon, because it doesn't need to handle this request. The dispatcher thread is not responsible to find the search for the desirable content uh, 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 based on the web page cache or the database. They don't need to. Excuse me. So the dispatcher thread it's not responsible for the concrete behaviors to check the database or the web page cache. So it's very soon for the dispatcher to just hand the hand the request to a certain worker thread, and after that, we can see there are multiple worker threads in this web service process. After it gets the request from the dispatcher thread, it just runs its own instructions, maybe in different, maybe in a separated physical CPU. Because usually there are multiple CPU and there are multiple CPUs in the server of a website. So during the same time, during the same time that multiple worker threads are checking the web page cache, or maybe sometimes they need to check the database of the website to get the desired content. During this same period, the dispatcher thread can just can get or respond to a lot of requests. After the worker thread get the data that the request is that the request requires, then the worker thread just hand the data back to the process, and it can and the users can get the response much faster. Because if there is only one, there are no more, there are no multiple worker threads who handles multiple requests at the same time during the same period. All the users access to this same website, they have to get their request response one after another. They can't get their response in a parallel way, because I think you just get it, right? So we just use multiple worker threads to handle multiple different requests from the users around the world, and so the users can get their response very fast, faster the single uh, than the single process. And after we understand the situation with multiple threads in a process, we need to focus on these two lines, on these two sentences, because this is very important for you to understand it. It's just a common sense for the students majored in computer science. You must know that processes are the entities for resources allocation. So it means the operating system allocates the memory, allocate the address space to a process, but not a thread. It means the operating system uh, allocates any I/O device or or the file, the access to the file to a process, but not a thread. And also you need to know threads are the entities for CPU scheduling. It means when if there are multiple threads in the same process, the basic scheduling unit is a thread but not a process, because there are multiple threads in the same process. If the process has permission to use CPU, it has to decide which thread in this process can can use that CPU. So processes are for resource allocation, threads are for CPU scheduling. You just need to memorize these two important tips. And also, if you check the relevant information about threads and processes, you can see all the threads, they just share the same address space of the process, right? So it means the global variables, the open files, and even the child processes of the same process, all of this information are the same for different threads in the same process. But this four kinds of information, they are different. It means all the threads have the same information on the left column, but they have different information on the right column. You can see because the threads have different instructions, have different codes to be put into CPU to run, to execute. It has to record its own program counting number. Because if we recall the example about the word, the thread responsible for the inputting, for the typing, it has to record the next instruction is 1000, and for the thread responsible for the outputting, for the backup, for the saving, it maybe the number in the program counter register is 100. So they have different instructions to execute. Of course, the threads have to record the different number in their own programmer counter. Also, you can see the registers, the general registers for the data, and the stack, and the states. Even the states, they are different. Maybe the first thread is if the first thread is in the running, it's highly possible that the second thread is ready, and the third thread is blocked. So it can have different stats. The different threads can have different states, different stack registers, program, counter, content, but they have exactly the same address space and the files and child processors, etc. So that's all about the threads you need to know. The last part is about this popular POSIX threads. It's just a standard for threads proposed by IEEE. If you are interested in the complication of the thread, or the you can check the this standard after the class, because there are there are many different thread core in the standard responsible for different things. You can see we have the this core to create a thread, just like we need to use a fork to create a process. Anyway, if you're interested in this part, you can check the relevant information after the class. But again, on this course, we usually don't talk about the implementation details a lot. We just focus on the principles. After at the end of this semester, you are you are supposed to build a complete framework about how the operating system work, how the operating system manage kinds of the hardware and software resources. But you don't need to focus on the implementation details. You don't need to check the open source code. You just understand the basic principles and concepts and methods and the algorithms. It's enough for this course. Okay, so now let's move on to the important part of this chapter and maybe the most difficult part in this chapter. It's about inter-process communication, IPC. So you can see there are lots of content to learn. First, I have to explain the structure list here. First, we should understand what kind of job is relevant to the IPC. Basically, it has we can divide it into three types. If if the relevant processes they need to communicate each other, sometimes they just need to send a simple message to each other. Maybe process A send some message to process B. You need to transfer some data to process B. This is the simple one. And besides, the processes, they need to, how to say, they need to coordinate to finish a job together, or they need to compete for some key resource. So we can say this are synchronization and mutual exclusion. There are two, besides the message passing, the other two types of IPC are called mutex exclusion and synchronization. For the mutual exclusion, it means you need to the two or more processes, they have to compete to use a shared resource. Maybe this shared resource is just some shared data or shared file or a shared hardware resource. Anyway, if two or more resources, they are compete for something, they need to use this shared resource one after another. Then we call then we should put them in a mutual exclusion way to handle to execute their own different code. And if they need to cooperation, if they need to cooperate to finish the job, for example, if process A needs to receive needs to do something after process B finish some other things, process A has to wait for process B to finish that job, then process A can continue process A's job. We call it cooperation, we call it synchronization. So for these two cases, the solutions are kind of complicated rather than much more than the first case. The first case is only about to pass messaging, pass message among the process. It's comparatively simply, but it's comparatively simple. But if you want to handle the last two cases, you have to put more attention on the methods and and how to understand the methods to handle the last two cases. You need to understand these two basic concepts first, these terms. You need to know that the risk conditions might emerge when more than one, when multiple processes shared a certain resource, and it might cause some errors. So we should avoid such errors from happening. And how to avoid this? We should use some solution. We should we should prevent the multiple processes to share a certain resource. We should prevent them from getting into their own critical regions. So you have to understand what is so-called critical regions. So multiple processes, they need to share a certain resource, and they need to get in their critical region one after another. They can't stay in their relevant critical regions during the same time. So that's the key to solve the to handle this issue related to the last two cases. And after we understand the problem to be solved based on these two parts, we're gonna propose some possible solutions. So the first two parts is about the problem description, and these two parts, part 3 and part 4, in these two parts, we can will see a lot of proposals or a lot of solutions trying to solve this issue. But for kinds of reasons, they have kinds of disadvantages or defections. So these two parts, you can take it as the failed try. And for these three parts, it can be successfully used to handle the issues. However, we just need to focus on the on part 5, semaphores. Semaphores are very they are the key concepts for the operating system for this course. So basically, in this section, you will learn what's the problem to be solved based on these two parts, and you should focus on this part to get the way to solve this problem in a proper way. And in the section 5, the classical IPC problems will just use this mechanism, use these semaphores to handle some classical IPC problems. So it's very important for you to understand what the problem is, what the issue is, and then understand the basic solution, the basic idea or the basic mechanism to solve that kind of issue. And for the other parts, you don't need to, I don't think you need to grasp them for 100%, but it's very useful for you to understand some specific proposals in this part, because based on this failure, you can avoid the similar failure in the future. So again, this part, part 3, part 4, part 6, part 7, part 3 and part 4 are about some failed try. 6, 7, they are about some success try, but they are not the important part for these sections, but they are useful for maybe useful for the work in the future. So I suggest you to at least understand the idea, understand the ideas relevant to this 4 parts, part 3, part 4, part 6, and 7. So that's basically about that's basically the explanation about the structure inside this section. So now let's move on to the problem description. So first you can see there are multiple processes in the same computer, right? And they need to communicate with each other. And we just explained this about these 3 IPC issues. The first one is comparatively simple to handle because we just need to pass the information from one process to another. There are some successful solution for us to just follow it. We just need to follow it and use it, and we can send the message among processes, and this part will be discussed in the last in the end of this this section. The difficult part is about the last 2 issues. Actually, if you understand the real meaning of these 2 issues, you will see the second issue is a special case of the third issue. But here we just list them in 2 separated issues. Because this one, the second one is how to say, it's just spatial. You just need to understand mutual exclusion means you need to make sure, you have to ensure 2 or more processes do not get in each other's way. How to understand this expression? It just means if mutual exclusion needs to control or needs to manage more than one processes cannot get in their relevant critical regions during the same period. So all of this is about the critical regions, the second part. We just think we just explain it a lot on this slide, right? You have to understand what's critical regions for multiple processes. And mutual exclusion means you cannot allow multiple relevant processes get in their own critical regions during the same time. That means every for some relevant processes, they want to get into their critical regions. Okay, but you can only get into your own critical region one after another. If process A is in its critical region, then process B has to stay out of its critical region. So this is the essential problem about mutual exclusion, the second issue about the IPC. And the last issue is how to achieve proper sequencing when dependencies are present. This is just the case. We said process A needs to do something after process B finish something. If process B doesn't finish that job, then process A has to wait. Process A cannot continue doing anything until process B finish its job. So at this time, a process needs to wait for some events which can be emitted by another process. And this case is called synchronization. And if you think it over, you can see that mutual exclusion basically is a spatial waiting, right? It's a special case about waiting, because process A needs to get in. If we suppose two processes, they need to get into their critical regions. If process B is already in critical region, then process A has to wait until process B get out of process B's critical region. Then then process A can get into process A's critical region. So basically, you can take the mutual exclusion as a spatial synchronization. Also, these two issues, they are basically the same thing about how to cooperate the different execution order among multiple relevant processes. So these are the very difficult part, very complicated part for this course. The first part, we just need to take a quick look about it at the end of the section. So for the whole section 3, we need to focus on this synchronization issue. So first, we need to figure out what the problem is, what the issue, what the problem to be solved is, based on the race conditions and the critical regions, based on these two terms. So what's race conditions? Race conditions happen or emerge when two or more processes are reading or writing some shared data. So here, it means these two or more processes, they are sharing a software resource, and that software resource is some shared data. So if two or more processes, they are reading or writing some shared data, and the final result of this of these two or more processes depends on the execution order of the instructions, then the race conditions emerge. So you can see if the key factor about this race conditions are here. So the different execution order of multiple processes, the different execution order will bring different results. That's the key. But you'll see for a given program, no matter how many times we execute it, we are the same. We just expect the same result, right? You execute it 100 times, 1,000 times, or even million times, the final result should be the same. That's the right situation, right? But if two or more processes, of course, they are relevant to two or more programs. If multiple processes, they execute in a different order in the same CPU, and they can get different results, then something is wrong, right? Then the errors just happen. So we should avoid that case. We should avoid the race conditions. We shouldn't let the different execution order affect the or we put it this way, we shouldn't let the execution order generate different final results, no matter which order, no matter which candle of order the multiple processes take, they have to generate exactly the same final result. That's what we want. And how to get this situation, we should avoid the risk conditions. And how to avoid the risk conditions, we should manage all the relevant processes. We should manage them, get in their own critical regions in different time, one after another. These multiple processes, they can't stay in critical region during the same period. That's the key. So let's just understand this problem through this concrete example. Okay, this is very important. So now I'm just explain the synchronization issue based on this example. I need all of you to focus on this example. I'm gonna ask some questions during when I explained about this example, about the I'm gonna asking some questions about the value of this variable x. So I need you to answer these questions. So from now on, you need to focus and you need to understand the problem, and you need to give me the right value of this spatial shared data called X. Okay, so now let's begin. We just suppose that we need to order some tickets. Maybe it's flight ticket, whatever. We need to order some tickets, and of course, if you want to order some tickets on internet, on the website, you have to access that website. You have to have to submit your request, right? And on the server of that website, it has to handle all the requests from the different users around the world. And we just see we just let X we let X represent the number of the tickets. Okay, so we suppose in the beginning X, you can check the let me see. So I just type some information in the discussion area. You can see that, right? So let's suppose in the beginning the initial value of X is 3, and then there are two users want to order the tickets, process A and process B. So if you if the two processes, they are executed one after another. I mean, after process A order one ticket, then process B come to access the website to order the next one. Then X should be 1, right? After process A gets one ticket, the X is 2. X should be set as 2. After process B ordered one ticket, then X should be should be set as 1. So this is the right result, right? But now we'll see how the different execution order of these two processes influence the final result. How can it be just 2 after 2 processes order one ticket separately? So now we suppose, just follow me to check the whole process. First, we suppose process A check X, and it will judge if X is greater than 0, right? So after this instruction is executed, the X on the server is 3, right? In the beginning, X is 3. Nothing here, process A read X and then write X. Process B just do this exactly the same thing, read X and then write X. But if the execution order is changed like this, if process A executed these two instructions and get X is 3, and at this point, it's possible for process B to be chosen to use the CPU. It's possible at this point, process A has to get out of CPU and let process B get in to execute some instructions from process B, right? So at this point, X on the server is 3, and then process B check X, read X, and get X is 3 is greater than 0, and then process B execute the next instruction, and in process B, the last instruction is executed and X is written as 2 because X is 3 before we subtract 1 from it. So 3 minus 1 is 2. Very simple, right? And after that, so I just draw a line after the we draw a line, draw 2 lines under the instructions we just executed, and I circled this instruction. We haven't executed this circled instruction yet. So here is a question. I need you to tell me, after this circled instruction is executed, what's the value of X? You just need to type the answer in the discussion area. If no one submits your answers, I'm gonna ask someone to do this. Okay, so let's from I don't know who to I don't know to choose who. Okay, how about Betty? Is Betty here? Is Betty here? I just so I check you are in the class, but you can't hear me. Are you there, Betty? Laptop? Laptop. Okay, okay, okay. Russell, you think X should be 1, right? Thank you for submitting your answer here. Thank you for the interaction. Okay, so, but have you ever thought that in process A, at this point, you just check the slide. I am drawing the lines here. At this point, process A is interrupted by process B, right? And at this point, what's the value of X for process A? Process A just check the value of X, read X, and get X is 3. When process A check the value of X, X is 3, right? And after that, before process A write back this X minus 1 to to X. When process A want to order a ticket and it checks the number is 3, so after process A ordered one ticket, X should be set as 2, right? But before process A executes this instruction, process A is interrupted by process B. Process B just get into the CPU and run all of the 3 instructions and put X as 2, right? Yes, yes, someone, oh, I'm so glad that some of you recognize the right answers, because in process A, it has no idea that X is already set as 2 after process B ordered one ticket. In process A, it just knows that X is 3 before it gets interrupted. So when it gets CPU back, X will be in process A. After it gets the CPU back, it just continue to the next instruction according to the program counter. It won't check the X again. It just continue to execute the next instruction, and X should be 2 in process A. 2, right? Because for process A, it just knows X is 3, and now I need to finish the last instruction. So X should be set as 3 minus 1 is 2. And now you see the problem, right? Process A and process B, they both ordered one ticket, and the X should be set as 1. But the different execution order of the 6 simple instructions made the final result as a wrong number. After process A and process B finish all of their instructions, X is 2 but not 1. So error happens, and we should avoid this kind of error, this kind of bug, right? So the key issue is to forbid more than one processes get into their critical regions during the same time. So you can see if what's the critical region based on this simple example. You can see these three instructions are called the critical region for process A. Why it's called critical regions? Because they shared this data X. They both need to read and write to this X, and during one process is already read or write to this value, to this variable, the other processes need to read or write on this shared data. They are not allowed to read, to get into their critical regions to access this shared variable, to access to this shared data. If we can make sure that process A, when process A, during the process A is executing these 3 instructions, the other processes cannot access X. They cannot get in their critical regions to read X or write X. Then the final result will be the same result, will be the right value all the time, right? So that's the that's the issue. That's the problem we need to solve. That's the situation we need to ensure. We need to make sure this happens. So this example is very example, but it's very important for us to understanding the whole problem which will be solved in this section. And as I said, I emphasize it a lot of time. If you can understand the methods in this section, you can understand all the other methods or principles on this course because it's the most difficult one. So first we need to figure out what the problem is. And now we can move on to the next the part. There is another example about the print spooler. It has the same situation. It has the in this example you can see the same situation might happen. The same error might happen because if you want to print some files on the same printer, we can suppose there is only one printer in the room and multiple computers are connected to this printer. And then which file should be printed first and which one should be the next? It's decided by the printer daemon. And this printer daemon, it just checked a spatial spooler directory to get the file one after another. You can check this directory, this spooler directory. Any processes they want to print any files, they need to put the files into this spooler directory, and there are two how to say two important variables to record which to record the next idle slot and the next slot to be printed. In this example, in this figure, you can see if some processes want to put a new file to be printed, it should put the file into this slot, because in this data is set as 7. In and out, they are these two variables. They are shared by all the processes which need to print files on the same printer. So multiple processes, they are sharing a data. They need to read and write on this shared data, and then the different execution order among these processes might cause problem, might cause errors. Let's see what happened on this case. So this is the initial state, right? First, out is set as 4. It means ABC, this file will be printed next. And this slot is used to store for the next new file to be printed. And then we just suppose that process A and process B, these two processes, they both need to submit some files to print. And we suppose the execution order is like this. Of course, there are a lot of other possible execution orders, but in this order, let's see what happens. Process A reads in and stores the value 7. That's the initial value of in is set as 7. Of course, process A gets 7, and process A put it in a local variable to show the slot for the file is 7, and then CPU switches to process B. So now process A has no chance to execute the following instructions, because CPU just switches to process B, and process B will do exactly the same thing. Check the value of in and put it into this local variable, and at this instant, process A is out of CPU, process B is in CPU, and both processes, they think the next available slot is 7. And then B is still in CPU, so it can just do the concrete behavior to put the put its file in slot 7 and updates. Cause you already process B already put a file in this idle slots, and process B needs to be responsible to update IN to be 8, so that the next processor, so that the next process they can they know that the next idle slot is 8, but not 7, because 7 is used by process B. Process B now just put its own file in slot 7. Also, it's all normal by now. But then CPU switches to process A. Because process B just finished all its job, right? It checks the next slot number, it's 7, and it puts process B puts its file in slot 7 and then change the in as 8. All the jobs are done, and then process A will continue the next two steps. It means process A needs to put its file in slot 7, because when A checks the value of in it's 7, right? Process A has no idea process B already put its file, put process B's file in slot 7. Process A has no idea about this. So process A just overrides the file in slot 7. The file from process B is disappeared, is erased. But process B has no idea about this. Process B just finished its job and leave this directory and do its next jobs. So the final result is process A gets its file printed, but process B has never gotten its file printed, because it's already erased by or overwritten by the file from process A, right? So this is not what we want when we share the same set of resources in the computer. So the operating system, or maybe for the application programmers, they need to consider this kind of case. They need to consider all the possible similar synchronization problem. But basically speaking, it's impossible to consider all the cases. We can always try to avoid such errors happen, but we cannot just we cannot just do the best job, because there are always bugs in the program. But at least we need to understand this case, right? We need to understand there are some risk conditions to be avoided. There are some mutual exclusion or the synchronization issues we need to handle, we need to solve, and we'll try our best to avoid them. As long as we are trying, we can decrease the bugs of the programs. So how to avoid risk conditions? And you might recall what risk conditions are. When multiple processes, they need to access a shared data, and the different execution order of them might bring different final results. Then the risk conditions happen. We should avoid these risk conditions. And how to do that, how to make this happen? We should make all the processes, all the relevant processes, make them execute in a mutual exclusion way. And this mutual exclusion way means if one process is using a shared variable or file, then the other processes will be excluded from doing the same thing. It just means if multiple processes need to read or write, need to access a shared variable or file, they need to finish this job one after another. They can't do this job during the same time. Okay, so it means when process A is doing this job, it has to, or the operating system or the programmer needs to design the code to finish this job to prevent other processes from accessing the shared variable or file, right? So how to finish it, how to finish this job? We need to make sure that all the related processes, they can get into their own critical regions separately at a different time, or exclusively. So first here we are we should discuss this term, critical region. So what critical region or critical section is? It's the part of the program where the shared memory is accessed. And this is called the critical region or critical section. You just recall the very simple ticket ordering example, right? Process A, process B, they just need to finish 3 simple steps. Read X and judge and compare it with 0, and then write X. These 3 simple steps, they all together just form a critical region, because these 3 instructions, they are the part of the program where the shared, here is not shared memory, a shared variable is accessed. So from the first instruction to access the shared data or file, you just need to draw an abstract line before that instruction. And after you finish all the access behavior on the shared data or file, you can draw an abstraction line after that instructions. And between these 2 lines, there are critical region for this process. Each process, because there are multiple processes, they need to share some data or files, right? Each process, they have their own code to access that shared data or file, and each process has its own critical regions. If one process is already in its critical region, it means this process is already executing some instructions relevant to the shared data access. At this time, all the other processes relevant to the same shared data or file, they are not allowed to get into their relevant critical regions to access the shared data or files. Okay, you need to understand those words first, and then you can figure out the solution to handle this issue. So how to make sure that no 2 or more processes in the critical regions at the same time, so as to avoid risks? Oh, we should, here we just list 4 conditions. We should make sure that these 4 conditions are satisfied. These are just theory to make sure that the multiple processes are, to make sure the not allowed to get in the critical regions at the same time. And these theories can help us to understand the real purposes, the real solutions. So we just take a close look at these four conditions. First, you need to satisfy this condition. No two processes may be simultaneously inside their critical regions. Oh, it's just like some repeated word. Okay, so this condition must be satisfied. So during the execution of multiple processes, no more than one processes can be simultaneously inside their critical region. It just repeats the problem again. And no assumptions. Here is the second condition. No assumptions may be made about speeds or the number of CPUs. So you can't suppose there is only one CPU. It means a lot. If you suppose there is only one CPU, maybe you can just let the other processes have no, you can make the others not have not chosen by the scheduler to get into the CPU before process get out of its critical region, right? But you can't assume there is only one CPU. If process A is in its critical region in CPU 1, maybe if there are multiple CPUs in the same computer, maybe process B can do the same thing in CPU 2, right? So you can't just figure out a solution about the CPU's usage control to solve this issue, of synchronization or mutual exclusion. There are no assumptions about the number of CPUs. Also, there are no assumptions about the speed. The speed means maybe you can assume that the speed is very soon before it's just very fast for a process to run all the instructions in the critical region. So it doesn't need to worry about get interrupted by another process, and that process will get in its own critical region, and so more than one processes are in the critical regions. You can't assume that the speed or the speed to execute the instruction is so fast that there is no chance for the other processes to interrupt the process which is already in the critical region. So this is about the second condition. And the third condition says no process running outside its critical region may block any processes. What does this mean? It means if you are not in your critical region, if you are not access that shared data or file, you cannot forbid some other processes from getting in their own critical regions. You know what I mean? I mean, only the processes in the critical region, or if you are not in the, it's just literally this sentence says the meaning. If this process is outside its critical region, it cannot block any other processes. It cannot forbid any other processes from getting in their own critical regions. And the fourth conditions are is no process should have to wait forever to enter its critical region. It means sooner or later, all the processes need to get in their own critical regions, should finally get in their critical region. You cannot let them wait forever. There is always chance for them to get in their critical regions finally. So these are four conditions we have to meet, we have to satisfy when we face this issue. But as I said, this just theories. how to make sure that these four conditions are satisfied. It's hard for us to prove them. We just need to focus on some possible proposals, possible solutions, and try to understand those solutions. Try to understand why they can solve the problem successfully, or why they cannot solve this problem successfully. And before we move on to the concrete solutions, we can check this figure to understand deeper about this problem. So here are two processes. Of course, you can see they are supposed to share a certain data or a certain file. And when process A is already in its related critical region, this gray box, this gray rectangles means process A is executing some instructions to access the shared data or file with and this data and the file they are shared with process B, right? If process A is already access the shared data or file, then when process B wants to enter process B's critical region, when process B during this period, if process B attempts to enter critical region, it has to wait. When a process has to wait for something, it will be blocked. We just talked about this in the last class among the transitions among four states, if you remember. B wants to get in the critical region, but he cannot. But process B cannot at this time because process A is already in it. So process B has to wait. As long as you need to wait for something, you are blocked. The state of process B will be set as blocked, and when the event that process B is waiting for really happens, then the process B will be awake or will be not set as blocked state any longer. So at this time, when process A leaves critical region, process B is not blocked anymore, and process B can get into its own critical region to use these instructions in the critical region to access the shared data or file. So these are the basic correct ways to share a data between two processes by forbidding one processes get into its critical region while some other processes are already in their critical regions, while the other process is already accessing this shared data or file. So process B or the second process, they are not allowed to get into critical region. That means only one process can be in the critical region at a time. During the same time, there are no more than one processes stay in the critical region. So we can check it very clear through this figure. And now let's we just figure out. I think if you follow the explanation, you might already get what the issue is. You already know what we need to solve, what problem we need to solve. And now we're gonna check some, how to say, some possible proposals to solve this issue. But you will see they have this defect or that disadvantage is that they usually don't use them in the real system. But we need to understand the basic principles, especially when the analysis about the solutions are relevant to the different execution order. I hope you all can understand what it looks like when the multiple processes have different execution order. You have to understand this, then you can understand a lot of things relevant to the operating system. So now, I think we don't have much time to explain the solution. Okay, let's just take a quick look. Okay, so the first one is about disabling interrupts. Interrupts. I emphasize this concept a lot of time. If you disable interrupt, that means CPU won't be notified that something, some events are happening, and CPU needs to handle those interrupt. No interrupt, no switch. Okay, no interrupt, then CPU will just let the process inside it keep executing all the instructions they need. So this idea of this first proposal is to disable interrupts when a certain process is in its critical region. And during the time when this process is in its critical region, no interrupts can be sent to CPU, no interrupts can be handled, then no switch happens. The CPU will be never allocated to another process, because we just talked about this. If the CPU needs to choose another process to use the CPU instead of the last process in CPU, it has to be triggered by some events. Either maybe the process in CPU is set as blocked, so CPU is idle, then CPU can choose the next one. Or the clock interrupt happens and let the CPU know that the time slot allocated to the last process is done, is up. Then CPU should choose another process to get into CPU. Anyway, there are some occasions that CPU to call the scheduler to choose another process to use CPU. So if there are no interrupts, no such switch happens. Of course, if this process just forbidden, all the other processes get into CPU, the other processes will have no chance to get in their critical regions, right? Obviously. So this method sounds available, sounds like this method can work, but we cannot choose this way, because it's very unwise to give user processes the power to turn off the interrupts. It will just cause a lot of problems, because you can see in the we never we never give the user processes or the application programs more rights or power to do things which can be done by operating systems. It will cost a lot of time. If you are interested, you can check the details in the textbook, because it's not so important. And also, we just explained about the second condition, right? If you still remember, there are no assumptions about the number of CPUs. If you just disable the interrupt for this CPU where you are in, where this process in, you cannot disable the other CPUs in the same computer. So the other processes, they can get in their critical region. They can run some execution instructions. They can execute some instructions in their critical regions in another CPU. So you can see this way is not adopted. It's just a assumption. It's just a failed proposal. And then we can check the, we can set a single shared variables, and we set the initial value as 0, and when the lock, each process wants to enter its critical region, should check the value of the lock first. If the lock is 0, it means no processes is in its critical region. So if the lock is 0, it means it's unlocked. Then you can get in your critical region. But if you check the lock, the lock is 1, and it means there is already another process in its critical region. So it means this variable just is locked. The critical region is locked. So if you check the value of the lock, it's 0, you can get in. It's the 1, you cannot get in. You will be blocked. You have to wait outside of your critical region. And this sounds available, but it's not adopted. It's not adopted either in the real world, in the real system, because it has these defects. Because you can check the defects after the class. We just we just jump over this part. If you are interested, you can check. It's also related to the switch between the or among multiple processes, because you can't make sure that this process A can stay in CPU all the time. Maybe after it checks the value of the lock and found it's 0, and right before it gets into its critical region, the CPU is allocated to another process. So process A can not actually get into its critical region. And then the other process might get CPU and check the lock is 0 and get in its critical region. And when the CPU is back to process A will get into its critical region by mistake. Anyway, if you are interested in this, you can check it after the class. So that's all for today's class. And in next class, yes, time is out. The 3:30, right? Oh, I just wrong. I just calculate in the wrong way. 95. Yes, sorry. I made this mistake twice. I think the first class I just think the time should be 15:30. And for today, it should be 11:20, right? Sorry. Anyway, the last 10 minutes I just explained in this class. It's not so important. So if you are, you can totally ignore the last 10 minutes. I'm sorry about the wrong time. I'll notice it next time. Okay. So let me check this with you together. It's right. These are the correct time to dismiss you, right? 15:15 for the class in afternoon. Yes, sorry. I just made this mistake more than once. I'm really sorry about that. I hope you're fine with this. Okay, if you have any questions, you can ask me after the class. And for today, you just need to focus on the problem description of this section. Okay, that's all. Oh, I don't know if I can occupy your time for one more minute, because some students just asked me these questions about the assignments. If you check the last slide in the, I can't just move on to the last slide. if you check the last slide, you can see the assignments of this chapter, and you only need to submit the chapter after we start learning chapter 3. So if you want to finish the assignments in advance, you can do it now. Everyone is free to leave, okay? I'm sorry again. Okay, bye. Thank you for thank you for letting me know that the wrong time. Okay, I'll notice it next time. Maybe I should set the alarm clock. I don't know. I'm not sure. Okay, see you next time, next week. Okay, because we don't have class on this Friday. See you next Monday. Bye.